Hi everyone, today I'll show you how to process MLCCs without nitric acid. This is not a tutorial, do not repeat anything shown in the video. While most MLCCs are based on barium titanate, there are some that are made with mixed metal oxide ceramic. This means the ceramic can be dissolved with mineral acids that do not dissolve silver and palladium. This video is part 1 of a two-part series in which I will extract from MLCCs not only silver and palladium, but also zinc, cobalt, manganese, tin and nickel. The downside of this process is that it only works on MLCCs with mixed metal oxide ceramic. It does not work for MLCCs with barium titanate or any other type of ceramic that does not dissolve in hydrochloric acid. Most common way of processing MLCCs for the precious metal content is crushing them and leaching them with nitric acid. Nitric acid dissolves the termination contacts and the internal electrode. This works well regardless of the type of the ceramic used, but mixed metal oxide ceramic also dissolves in nitric acid, so you have to use significantly more of it than when processing MLCCs with more inert types of ceramic. So, I had an idea. Why not just dissolve the ceramic and entirely eliminate the need for nitric acid? Nitric acid can be expensive, and its sale is highly regulated in many countries. In contrast, you can buy dirt cheap muriatic acid, that is hydrochloric acid, basically everywhere. For this test, I weighed out 100 grams of mixed metal oxide ceramic MLCCs and added to them 220 milliliters of 31% hydrochloric acid. Reaction with zinc oxide-based ceramic was exothermic, meaning the solution heated up. Because of that, and because of HCl vapors, such reaction should always be performed in a way that negates the dangers of spillage and corrosive gases. Ceramic began to break down very fast, and the solution turned greenish blue color. After 24 hours, the color is a striking reddish pink that is, interestingly enough, somewhat stratified, less intensive at the top of the solution. As you can see, some of the capacitors dissolved to the internal electrode. I'll stir the solution a bit and let it sit for another day. So far, the approach seems to be working. After thoroughly stirring it, I left the solution to react for another day. After 2 days, the ceramic fell apart into yellowish powder, and the solution became even more intense reddish color. While the color is strongly reminiscent of palladium chloride, only a very small amount of it should be present in solution. I believe the color is due to a mix of cobalt, nickel and manganese chlorides. After I was done dissolving the ceramic, I decanted the solution, filtered off the undissolved ceramic powder, and thoroughly washed the remaining metal. As you can see, I managed to remove pretty much all of the ceramic. All that was left of a majority of capacitors was only the internal electrode and the termination caps. There might still be some undissolved nickel, but this isn't much of a problem because there wasn't much of it to start with. Nickel is only present as a very thin plating atop the termination paste. At this stage, what remains of the capacitors can be refined further, or it can be melted down and sold to a refinery. All of this depends on whether they're ready to properly compensate you for the palladium content in the silver. Ideally, I would melt the palladium silver alloy in an electric or gas furnace, but since I do not own either of these things, a beat up fire brick and a MAP gas torch will have to do. To remove any potential zinc, tin or ceramic impurities, I added an oxidative flux made of 5 parts borax and 1 part potassium nitrate by weight. I had to switch to smaller portions because I couldn't melt all of it at once. I did not expect that because I had once successfully melted close to an ounce of silver with the same setup. I had either added way too much flux or this alloy has noticeably higher melting point. After going through all of the material and collecting all of the bits and pieces of silver palladium alloy, I was left with 6.8 grams. That is 6.8% of the starting mass. I believe this method works very well. I only need to get better equipment for the smelting part. Stay tuned for the part 2, in which I will recover all of the metals left in the solution. Thank you for watching, like, subscribe, and see you next week.